Today we're going to be talking about how to find the smallest distance between a point and a plane. And in this particular problem, we've been given the coordinate point 2, 1, 1, and the equation of the plane x plus 2y plus 2z equals 11. Now, because we're trying to find the minimum distance, the smallest distance, we can look at this as an optimization problem. But when we're finding the smallest distance between a point and a plane, really all we're going to do is use this formula here for d, where d is distance. This is a formula we can use in this exact scenario where we have a point and a plane and we're talking about the distance between the two. So when we recognize that we have that kind of a problem, what we're looking for is the equation of the plane in this format here, ax plus by plus cz plus d is equal to 0, and a particular point where we have the coordinates x sub 0, y sub 0, z sub 0. When we can identify those values, we can plug them into our formula for d, which is going to give us the smallest distance between the point and the plane. So the first thing we need to do is match up the values in our point and plane with a, b, c, d, and x sub 0, y sub 0, z sub 0. So if we go ahead and color code a couple of things, what we can see here is that we have x sub 0 here, we have y sub 0, which is going to be 1, and we have z sub 0 here, which is also going to be 1. So those are the three values in our coordinate point. Then we can also look here at the coefficients in our coordinate plane equation, and what we see is that the coefficient in front of the x variable here is 1, so that's going to be equal to a. We have the coefficient in front of y, which is 2, so that's going to be equal to b. And we have the coefficient in front of z equal to 2, so c is going to be equal to 2. Now notice here that we have plus d, which is supposed to represent our constant, but our constant is over here on the right-hand side. So all we need to do is take this constant, subtract 11 from both sides, we get 0 over here, and we get minus 11 now over on the left-hand side. So notice that the equation of our plane is equal to 0. That's what we want on the right-hand side, equal to 0. And now we can say that d is going to be equal to negative 11. It's really important that we include that negative sign so that we get the correct answer. And if you have a negative value in front of any of these coefficients on x, y, and z, we're going to want to include that negative value as well. So now that we've identified a, b, c, d, and x sub 0, y sub 0, and z sub 0, we can plug them into our distance formula. So for d, we're going to get d equals the absolute value. Notice we have these absolute value bars here. So we have the absolute value of a times x sub 0. Well, we know that a is 1, and we know that x sub 0 is 2, so we plug those in. Then we get b times y sub 0, so we have b, which is going to be equal to 2, and y sub 0, which is equal to 1, so 2 times 1. Then we have plus c times z sub 0. c is equal to 2, and z sub 0 is equal to 1, so we get that there. And then we have plus d. So we have plus a negative 11 because we know d is equal to negative 11. So we've got our absolute value bars. And then in the denominator, we have the square root of a squared. Well, a is 1, so we have 1 squared, plus b squared. b is 2, so we have 2 squared, plus c squared, where c is 2, so we have 2 squared here. And now it's just a matter of simplifying this as much as we can. So we're going to get d is equal to the absolute value of 2 plus 2 plus 2 minus 11, all divided by here the square root of 1 plus 4 plus 4. And we're just going to continue simplifying over here. So we're going to get d is equal to, here in the numerator in our absolute value bars, we've got 2 plus 2 plus 2 is 6, minus 11 is a negative 5. So we have the absolute value of negative 5. And in our denominator, we have 1 plus 4 plus 4 is 9, so we have the square root of 9. And when we simplify, of course, in the numerator, the absolute value of negative 5, that becomes a positive, so we get positive 5 in the numerator. Square root of 9 is 3. So we know that the smallest possible distance between the coordinate point 2, 1, 1 and the equation of this particular plane is 5/3.